Hello and welcome back to the lab. Today on the bench we have another piece of the TM500 series puzzle, a FG501. This is a 0.1 to 1 megahertz function generator from the TM500 series. This one's not mine. I was sent this and asked if I would give it a once over and get it ready for someone else's lab. Given what we have here, a cal sticker from 2021, where it's not even due until 2022, we're probably going to find a relatively functioning unit, and everything's going to be ready to go. But we'll give it a shot. We'll check it in, and we will see if it needs any help. If it does, we will get it going. But cosmetically, it's in great shape. Everything looks to be in good working order on this one. I do see some, just from looking in the back here, I see a couple caps I want to replace just to make this go the distance in the long haul. But, well, let's take the side panels off and take a quick look inside. These are relatively simple on the inside. Some op amps, raw transistors, this gearing here, that's not good. Okay, well that's broke. Our front knob is busted. That explains the screw that fell out when I was carrying this down into the lab. So I wonder if that's, no, it's not jammed up. But it's not happy either. These are the two main power supply caps, these 750 microfarad at 40 volts. I'll replace these for just to make it go the distance. These caps right here, these are Tektronix timing capacitors. These should not be changed unless they are confirmed bad, and triple check them before these get condemned, because the ratio between these three, this one on the back and this one right here, set up the multiplier for the front panel knob. So if these have to be changed, they used to be sold as a set. Obviously, getting them as a set in today's world is fairly difficult, but that could throw off one of the ranges for frequency accuracy if it's needed. Just something to know. So we have some tantalum capacitors up here. They look okay. This one may have a split in it, and we'll check him. Everything doesn't look too terrible. Should be safe to power up, so we'll go ahead and throw it in my diagnostic frame, and we'll just put a scope on it and see what happens. Hopefully it gives us some waveforms. This mechanical damage we will definitely need to fix. And I will have to talk to its owner, see if they want a new knob, because this knob has seen better days. We have a giant crack coming through here, a few others, but turns okay. It will function, it just won't look the best, but that's all right. All right, well, let's turn it on and see if we let out the magic smoke. So I have my frequency counter hooked up to the oscilloscope. That'll give us a check for the dial accuracy on how accurate that is. I'm not expecting extreme accuracy yet, but especially with the knob being messed up, I am roughly asking for about a kilohertz of, looks like a ramp. Let's do square wave, just because. So we'll ask it for a kilohertz square wave, and we'll just see what it does. Keep an eye on the scope. Well, that's a good shot right there. Boom, kilohertz. Let's see. Ooh, amplitude needs to be cleaned. Give my frequency counter a little bit of time to gate. Okay, we're at 1.7, and so it's pretty close. Let's see what that does. We'll put it right on 1. Actually, it's pretty accurate. 104, 1.0432, so that's not terrible. Amplitude is definitely crusty. Let's see, triangle wave? Not the... Well, it's a triangle wave. Definitely, we have some screaming, though. Or is that false triggering? That might be false triggering. No, it looks like we got some oscillation in the... have some oscillation in the triangle wave itself. See if we can't zoom in on that. Okay, well, let's check sine waves. Sine wave looks better. Where's my AA? Yeah, sine wave looks pretty good. Let's see what we have for distortion before we do any work. I'm not expecting super ultra low distortion out of this unit because this is a function generator. So that's not their claim to fame. This one's kind of nice because it has a little bit of pulse. I can do ramps on this one. We have square, sine, triangle, all of the wave shapes you would want out of a function generator. We can do VCF, voltage control frequency. We can also gate the pulse, and we have some trigger outs. So there's a lot this thing can do, especially for its time. From a distortion standpoint, 0.239% THD at 1 kilohertz. And that is with the high pass and the low pass filters turned on, which is not horrible. Now, there is no frequency distortion specified on the on this unit. I have to really check the spec sheet, but at least on the Tech Wiki, there's not anything jumping out at me. So, what are we going to attack first? So this block here is our DC offset switch, switch and control. So switch is in the back, controls here. We have our amplitude potentiometer here, which is going to need some service and cleaning. We're going to hit these caps, get these replaced with more of the same, maybe 1,000 microfarad, something like that. Bump up the microfarads a little bit. Definitely have to fix this control. This is a this is actually a Tech. Oh no, that's not good. Very unfortunate. The front holes on that are shattered. I do not know if the camera's going to pick this up, but these posts, which I believe are integrated in the front panel, the plastics have been shattered on those. So they're shorter than they should be. So I'll have to see what that is about. It very much looks like we have to disassemble a lot of the front to get this front panel off. So let's attack that first, because there's no sense in burning the caps and the parts if the plastic pieces can't be fixed and the frequency knob gets back to rights. So, all right, first things first. This is spinning when it shouldn't be. I need to see what's under here. So let me get this knob off and we'll start there. Okay, that could have been a lot worse. The dial, it looks like it's just a little loose on the front. So what we're going to do is we'll pop this nut off, and then we will see about removing the dial face. I could super glue these cracks just so they don't open up, and then I can tighten it back again, and then that'll be a I'll see if I can find some parts for this. I'd like to do a full restoration on it, but this plastic dial face is going to be hard to locate on I don't know if there's going to be a parts unit for one of these or not that I could get some stuff off of. But first things first, we will... Did I grab the right Allen key? Hey, look, first time. Starting to learn the screws that these things take. Here we go. Now we have these two Phillips screws, and this dial face is going to come off. Just like so. Now that is split almost completely. You can see the crack in it, but it's not quite cracked in half. So we might be able to salvage that. All right, here's the start of some of our problems. We'll keep going. This will have to come off. I'm also sure this will pop off. Not worried about alignments. Realigning these controls is actually fairly easy. No socket there, which is good. Oh, come on. There we go. There's that one. Okay, we do have a nut here that we're going to need to take off, which is okay, not a problem yet. Oh man, some of these are tight. All right, that'll just come off. See what this one does. I see another socket under here, so if I pull... Now, the theory is, if I pull these two sockets, do I need to take all the jacks off to get the front panel off? That's the question. The answer to which, at the moment, is I don't know. So, let's pull the nuts. Well, that's a big fat nope. It's going to be complete disassembly. So, I've got it loose, but it's binding up on the BNC jacks. So, I will have to get the BNCs out to continue with the disassembly. Now, here's the question. Are my micro wrenches big enough? Because these small size micro wrenches will make disassembly a lot easier if they fit. Nope. They are just shy. So I will need to go get bigger wrenches. Well, I'm kind of in, but I'm not. So there's a pile of parts over here to get this far. And as I was taking this apart, it really looked like somebody had done this before. I am not the first technician here. And I am pretty sure they got to this point and they stopped. Because this latch is locking this front plate in. But if we take a look, if I can get this camera angle right, this entire plastic piece that's on the back side of this is the support structure for this control. So this is a very strange design. If this was my unit, I would cut this and continue on. I'm already thinking about catting this up and maybe getting this done in metal. I don't know yet. But I'm definitely going to have to recreate this spacer piece if I want to bring this unit back. But since this isn't my unit and I'm not the owner of this one, I need to consult its owner. So we had to desolder these. You actually do need to desolder these legs and a few other things. So taking this thing apart is pretty involved. But I need to consult the owner and figure out where they would like to go. The plastic is just going to continue to degrade. So it's not, I could find longer bolts and just kind of fudge it. But one, that's not me. I don't like fixing things that way. But two, the plastic is already cracked once, and just from the color of the board and a few other things, I can tell this is an early unit. The caps kind of give it away. So the plastic's just going to continue to crack on this, and it's just going to degrade further. So if I'm going to fix it, I want to fix it right. Fixing it right is going to be quite involved, but I also need to talk to its owner and see what they would like me to do. So we'll see what happens, and we'll go from there. Okay, it's been a couple of days, and I have not heard back from the owner of this particular unit yet. So what we're going to do is, from conversations in the past, he's given me a pretty wide green light to get devices up and running for him. And so what we're going to do is we're going to go the non-destructive route. I was kind of bumming around the lab, and and it just kind of hit me how I could fix this control without taking this front panel off. So what we've done is we've wire wrapped the control. So this arm bolts to the metal through the plastic. I was thinking about 3D printing another front face with all the structures and things like that, but I was kind of worried about strength because this has to be really thin. I mean, you can see where the ear's gone. There's not much there. So from a 3D print, especially with all the layering and things like that, they're not strong when they get thin. They can be very strong. Excuse me. They can be very strong. I use 3D prints for feet for TM5000 frames and a few other things, and they can be very strong. But as they thin out, they get really, really weak, just because of the additive manufacturing process. So this allows me to take advantage of the metal, and this shouldn't fail again. It's wrapped in such a way where the control is not moving at all, and everything is good to go. I also took a lot of care to work this control in, grease the control, actually lubricate the control mechanically and electrically, and make sure it was good to go. This is a continuous pot. There's no stop in it, but it has a control to increase the friction. So when you turn the front of this, the pot doesn't move much, but it feels like you're turning a lot. This is done with ball bearings and some pressure gears, not gears, but puts pressure on the ball bearings and kind of just slows it down. It's a friction, almost like a limited slip control. You turn the front end, it slips a little bit to allow finer control of the circuitry without using a 10-turn pot. Reason being is we have this much frequency range in one rotation, so we need to slow it down a little bit so it's controllable. So a good quality oil and things like that, and this is a very free-moving control now, so there's not a lot of stress on the plastics. I do wish this was Feel-O-Vision, because a properly serviced control feels a lot better than a bound up one, that's for sure. So what I'm going to do is I'm going to get the front. I have a couple of the fronts because I was cleaning these controls. The amplitude, we know that was crusty from previous clips. I don't need the front face on here to do some preliminary testing because the frequency doesn't ultimately matter. So I'll put all the controls back in the front of the face because I don't need to take it apart now. And then we'll just check it with a scope, make sure the controls are behaving, things like that. Nothing's fluttering around. And at that point, we'll service these caps and then probably run this through an alignment, and we'll be pretty good to go. This kind of concerns me. I'm going to look and see if I can get another dial wheel because these cracks, I can sneak some cyanoacrylate glue in there to shore those up. The main problem is the holes are where the crack started, and it went that way. So I think somebody at some point over-tightened the dial face screws and blew the holes apart is probably what happened. But I am definitely not the first person in this unit, for sure. These plugs have been off before. I could tell by the scratching on the back and a couple of other things. So someone or a number of someones has had a go at this prior to it coming to our lab to get serviced. But yeah, all in all, let me get it to where I can electrically turn it back on again, and we will go from there. Okay, got the 2 output resistors hooked back up. This one is a pain in the butt to get tight and get on and get back on there, especially because it has this ground rail right here. So we have a ground rail, we have a rod, these 2 resistors, which are the output terminations, going to the output jack. Getting a tool large enough on here to get this nut tight is quite the pain. Okay, let's see if it gets to live again. We have, let's see, 3x of some random frequency. We'll give it about half amplitude. Scope set up pretty high. Let's see some traces. And we'll ask it for a sine wave just because we can. All right, we have sine wave. Not triggering, but that's the scope's problem, not the frequency counter. Okay, so we have a good sine wave. 7.948. Let's see if... So as I turn this control, we should see frequency changes, but we shouldn't see jumping around. So it should be a smooth progression, just like that. Now we're going to go off the end of the potentiometer, slow the clock way down. And then it's going to go off, and then it's going to come back at the high end. That's normal. And yeah, our potentiometer looks really healthy. All right, you guys can see the frequency counter. We'll wait for a gate. This is a very slow frequency counter, but 10.9. And looks like my dial face should be 11. So, yeah, we're good there. Oh, let's check amplitude as well. So we're about halfway up. Oh, that's much better. Yeah, that controls back to working well. All right, so we have really good triangle, square, ramp. Yeah, it's outputting everything it's supposed to. So we have really good electrical operation of this particular unit. So I'll get those 2 bulk filter caps replaced, and then I'll have to glue up this dial face, but I think this unit will live again. Okay, well, it turns out even in the obscene number of capacitors that I have in stock in the lab, I don't have a suitable replacement for these. They're 750 microfarads. I was thinking about putting in something around 1,000. But now the question is, what voltage is actually across these caps? So we have our meters hooked up. We're using these 2 meters in the meter bank, and 31 volts. Actually, supplies are relatively symmetric. So I need at least 35's kind of tight. I'd like 50. So I need about 1,000. Well, I need 1,000 microfarad caps at about 50 volts. Yeah, I've got 1,500 microfarads at 250 volts. 1,500's a little big for what I want to put in here, so I'll have to order some capacitors. No big deal. Through the magic of the camera, what will be an instant for you will be a couple of days for me. We'll just add it to the order. I have a board that I'm going to be designing on camera, possibly for those meters. I'm kicking around a circuit for battery elimination for some of those VTVMs. So we'll see how that goes as well. I'm going to order some caps. I'll have to put this on hold. But that'll also give me some time to glue up that dial face. And should be about it. All right. Glue is cured. Obviously, we have a little bit of crust we need to take care of. I've got these cracks shored up. Got the center crack shored up as well. And we fit back on the dial. No problem. Plenty of room. So the paper in the distilled water comes out, as well as the emery paper, and we need to buff this out. So this is what it looks like before I've gotten started buffing. Now, the nice thing on this dial is the numbers are on the bottom, so I don't need to worry about buffing those off because don't need to attack the bottom because the crack actually didn't go all the way through. But I do need to buff the top. So I'm just going to get started. It's a tedious, time-consuming process, but needs doing. So let me get the emery paper, and I'll bring you guys back during the process. Oh, I had to get a little more aggressive than the 800 grit. I had to go back down to 220. The 800 wasn't wasn't hammering the glue hard enough to really take the excess off. So dropped it down to 220, went back to 8, and this is 1,000 in emery paper, and we just buff this out. This is all it is, nothing special. Here we are finished up with 1,000, nice and cloudy, but also nice and uniform. This is not an easy piece to polish. We have a detent here where that comes out towards the back, probably to stiffen up the screw holes. But but I have to be really careful so when I'm pushing on the front, it doesn't flex this way and introduce more cracks. This is nice and smooth. The glue's actually doing a great job holding. But I do need to be conscious of, normally when I'm doing a meter face or something like that, I'm hammering a lot harder on the plastic. So this is taking longer than it normally does, but I don't want to introduce any more cracks in the dial plastic than is already there. So just taking time, getting it done. And here we are done with 1,500. Next up, 2,000. Okay, as we go up through the grits, it starts getting clearer and clearer because we're putting smaller and smaller scratches on the meter face. So at this point, it's ready for the buff wheel, but that's in the dirty side of the lab where the camera can't go. So I'm going to run this over the drill press, and I have a high-speed drill press that I have just a buffing disc in, and we're just going to buff out this plastic. And it should come clear. And all buffed out, we're nice and clear again. Good news is the cracks did not open back up, even on the buff wheel, so everything looks good there. And it's ready to go back on the front of the unit. Okay, I've got the dial face put back on. One of the problems prior to it hitting this bench was these two screws were put in way too tight, and that's one of the things that attributed to the dial plastic popping. To align the dial face, the screws only go in two ways, so it's this way or that way. I just used a frequency counter, checked it on the high end up here, 11 kilohertz, and that told me which way to orient the dial plastic, because if I orient it the other way, it's like 500 it's like 500 hertz. So dial plastic's now lined up. Everything's ready to go. Still waiting on those capacitors. We are dealing with a little bit of a holiday weekend, so extended time frames. Not sure when they're going to show up or not, but we're working through it. Everything is good on mechanically now. Everything is good on this unit, and it's ready to once I get those capacitors, we're ready for an alignment. Okay, and we had some capacitors show up. So, part number on these is focus. There we go, right there. They're UHE series, 1000 microfarads at 50 volts. Should be fine to replace these Mallorys. Let's see here, knife. Decent size, but not too overly large. So, I think those will work well. Smaller than the originals for sure. Let's get them in. Okay. This capacitor, this one right here, is not going to be an easy one to work on. The pin, or the through lead, is right here. And that actually comes up right in there. So getting the soldering iron in there without melting this coupler, this plastic piece, or this capacitor is going to be a trick. So on this one, I'm going to get at it from the top side of the board as opposed to the bottom. But it's what we got to do. And our new capacitors are in. Everything is good to go. So we're going to hook this up to a power supply. I need to let it burn in for a little bit. And as long as I did my job correctly, there should not be any excitement. All right, we're hooked up to a scope just to show some form of output. I'm using the Rigol for this. No big deal because I'm going to have this burning in for a long time. And no smoke, and I do have pulses. I don't want pulses, I want sine waves. So we will kick this over to sine waves. And we now have sine waves. Interestingly enough, though, not the cleanest sine waves, but that might be the speed. I'll slow it down and we'll see what we get. Yeah, we have just some distortion at the peak of the sine wave. Slow this down. I mean, that was fair. It was running fairly quick. Still have it. See what the distortion spec is. Let me warm up the 501. We'll see what we have going here. Seems fairly consistent, though. Well, it is performing fine within spec. The sine wave distortion is less than 0.5%, and we're at 0.254, so we're actually about half of the distortion spec. So everything looks good there. I'm going to set this back up on the scope. We're just going to let it burn in, and I'm going to leave it on for a while just to make sure there's no other issues with it. It doesn't, when it warms up, it doesn't kind of go crazy. So we'll see what happens there, and theory, we should be good to go. But I am going to put these old capacitors on the SMU and kind of see what their leakage was. I have set up the SMU to source voltage and measure current, and I've also set it to 4-wire measurement. So what we're going to do is we're going to source 40 volts, and we're going to ask it for 10 milliamps. So not a lot of current, so if anything goes sideways with the capacitor, it won't blow up or anything. But it'll at least give us an idea of the leakage, because the leakage of this capacitor should be in the microamps or the nanoamps. And we will just output on. And the capacitor was drawing more than... so yeah, we have some leakage. It's struggling to... Let me take this out of 4-wire mode, see if it behaves a little bit better. Okay, 5 milliamps at 40 volts in 2-wire mode. That's behaving better. Had to turn the measurement on. So we do see it falling with current, but we're still passing. It's struggling around 5-ish microamps. So definitely home menu measure. We'll make it 10 power line cycles. Slow it down a bit. Come back. Yeah, here we go. Now, as the cap slowly reforms, we'll see this trend down as we're getting to the end. But is 5 microamps excessive leakage? At 5 microamps, it would pass on the IT28. If I'm remembering the settings correctly. So it might be. One other thing to notice is as the 502 warmed up, the sine wave looks better. Still pointy at the end. Like this is from comparing this to like a 505. It's pretty sharp at the peaks of the sine wave. So that's where I'm picking up some of the distortion, I'm sure. And as expected, we have the downward trend of the current through the capacitor. Okay, the burn down test was successful. Nothing blew up. Everything was good. So it's now time to do an alignment. On this particular unit, we start with the negative 20 volt supply because that's the only adjustment. The other two supplies are referenced to it. And it's plus minus 1%. And I'm reading negative 20.138 on the 6500. So that looks good. So that's going to be within specs, so we don't need to adjust that. We do need to check the negative 17 and plus 17. The negative 17 and plus 17 are right down here, next to the ground test point on the bottom of the unit. Here's our plus 17. And our minus 17. And we want to check for ripple, so we're just going to AC couple this meter. This meter is plenty fast for looking at these units, and this actually wants a pretty quiet supply, so let's see what happens. We'll go to AC volts. That's actually good. Plus 17. Also good. We'll check the plus 20 supplies. There's our plus 20 volt ripple, even better. And our minus 20 volt ripple, even better. Spec is a ripple of less than 500 microvolts. So we're on the millivolt scale, so 0.5. Everything was good, very quiet, but this is a pretty tight power supply spec on a function generator. Okay, I'm set up to do symmetry, which is R170, and I'm going to cheat a little bit because I can use the plus duty cycle, minus duty cycle, and so I can use these 4 parameters to really dial in the symmetry. It's pretty close. It's off by 0.2%. So very much splitting hairs, which at 50 microseconds, that means it's off by 400 nanoseconds in terms of symmetry. So very good, but because we have the tools available, we're gonna see if we can adjust it a little bit better. The symmetry control I need to adjust is right here. It's this multi-turn potentiometer towards the bottom of the unit. And we'll use the camera to cheat, just because we can. And there we go. That's 50 and 50. So cannot argue about that. Very close. I needed to turn that 10-turn pot like a quarter turn. So, of this cluster of 3 potentiometers in the middle, we have sine wave drive and DC level. We're going to be adjusting these 2 potentiometers for minimum distortion, as noted on the distortion analyzer. This is done with the front panel at 1 Hertz setting with a multiplier of 10 to the 4. Okay, so we're going to tweak these 2 potentiometers for the lowest reading. Nope, that's going up. Ooh, that's coming way down. Okay, cool. Oh, we're going to get it better. It does say to check it multiple times because there's a lot of interaction between the 2 controls. I believe this is the DC level, is really touchy. But there we go, that's looking good. Then this is sine drive. 296 looks like it's going to be it. $295, $296. That's going to be it. Come on, give me back 299. You can see how touchy some of these controls are. There we go. All right, so we will leave it right there. Well, we're going to do this a little bit different. It wants us to adjust a sine wave visually on the scope. I've got an FFT function because they want to do it at 10 to the 6th. So we'll do it FFT'd into the DSA. Okay, doing the sine wave high frequency adjust. We're looking for the lowest value here at XTHD. Not much adjustment here. No, it is at 1. So it is on 1 by 6. This is a harmonic, and it looks like we have a harmonic here and a harmonic there. Let's see if we can't tune those out a bit. Okay, so this capacitor was not doing much on the top end of the waveform. It was just sliding a notch just right and left. And so it does not have a huge impact on the frequency, but we are at negative 25 dB. All right, we need to do triangle peaks now. So let's go back to the default waveform. Okay, looking at the triangle wave now. And that's going to look good. It's looking for triangle symmetry and linear slopes, and that's looking pretty good. See if any of these measurements make sense. Oh yeah, we can do rise time and fall time. $349. Yeah, that's close enough. Don't need to fiddle with that one. Okay, next up is the low frequency timing, which is going to be R105. This does need to be adjusted. So, where'd our tuning tool go? Must be a mechanic. This needs to be 11 kilohertz, so we're off by about 31 hertz. So, yeah, it is the 10X cal that's on the back side of the board. So we just dial that for 11. Well, I'm gonna call that there, and that is smashed against that is using the rubidium as a time base, so that's probably the most accurate clock this function generator's ever had. And we do have C158, so we go to 10 by 5. And a little light, not much. 3 kilohertz light on 1 megahertz. That's not too terrible. Oh, I forgot to do the 1x. So we got to go back to 10.3. There we go. Now we go down to 1. The frequency dial, and then we have to adjust R130 for 1 kilohertz, which we're running a little hot. And that's actually at the bottom. That was almost off a bit. It's on the mark. Some things weren't making sense, and now I know why. I cannot adjust the 1.1 megahertz on this one because the high dial top range is actually this timing capacitor right here. It's supposed to be adjustable, but this is a Tektronix capacitor. I'm not sure why this is here or has been over time. This is the low dial top range adjustment. This is the high dial top range. So this high dial one doesn't have a top range. Or I should say, this unit doesn't have a adjustment for the top range. But we need to do the low dial top range for 10 megahertz at 1. So we go up to that, and 1. All right, 10.002. So we're off by 2 kilohertz on 10 megahertz. And just bumping this control will swing it 100 hertz or 100 kilohertz one way or the other. Now I need to dial this up to here. And we are good. R460 for the triangle amp adjustment is hiding right down here. We're off by about 400 millivolts, so we want to get this exactly... Nope, we're going the wrong way. Triangle wave amplitude of 10 volts peak to peak, and we are good to go. We need to check the sine wave peak to peak, and we are at 10 volts exactly, so sine wave is also good. R255 needed to be adjusted for square wave amplitude. However, I was tweaking the wrong control for the distortion analysis, so I have to go back to the distortion meter, see if I can't clean that up a little bit better. But the pulse amp needed to be 10 volts. We're at 10 volts, but now back to the distortion meter. Okay, after walking the distortion back in, I've got 0.269, so we are better. We are checking the square wave compensation. This adjustment looks like it's going to be perfectly healthy on this unit. Everything is good to go, so nothing to adjust there. Okay, taking advantage of our 3585B, we have a 10 megahertz. Well, it's start frequency of 10 megahertz, ending frequency of 40 megahertz, so I can see the 11 megahertz fundamental and the first two harmonics. They need to be negative 30 dB down from the fundamental. And if I go to next peak, so we are at, there we go. I had to turn off auto ranging when I unplugged it because the levels changed on me. That's kind of annoying, but that's just this particular unit. So we're at 23.6 dBm of fundamental. And if we scroll over to the next peak, we are at negative 7.3 dBm. So we are at our negative 30 dB. And our next next harmonic down is negative 21.6 dBm, well below the 23 dBm fundamental, so that is going to be fine. Our DC balance needs some adjustment. This should be centered along the waveform, so we'll bring this down to, don't mind it moving left and right, that's just the trigger point moving. I just want to center the waveform over just to make triple check the scope is DC coupled, bandwidth limits off, and my reference line is the center line of the scope. So there we go. That was definitely off. My gating baseline could come up just a touch. It's not 100% perfect. So that's going to be R320. And right there. That's going to be good for the gating baseline. I did need to adjust my offset on my function generator. I'm using the 2102 for the gating square wave, but that puts a 2 volt peak to peak right around 0. I need 0 to 2 volts, so I had to put a 1 volt offset on the signal to bring it up to get the gating to work correctly. And we do get trigger out pulses, so that is working. And let's check the VCF. So what we will do is come here. All right. I'm gonna set up the, let's see. This is one of those things that's a little strange, so we're going to go to, and we'll run it at 1 kilohertz. But I actually want a sine wave, and I want 10 volts peak to peak. With a -5 VDC offset. Can it do it? I think it should be able to. Let's see what happens when we put that into the... Actually, we'll bring this down a touch to 5 volts peak to peak. So we'll get about a half swing on the frequency, but we should get a sweep pattern on the Rigol if everything works correctly. All right, let's check our VCO, or VCF, voltage control frequency, voltage control oscillator, VCO. Well, that looks good. So we're modulating, well, we're FM modulating at about a kilohertz, so our frequency modulation is working. Thanks for stopping by the lab and taking a look at this FG502 function generator from Tech. I'm actually not going to bill for this one. It's the restoration. The device works, but it's not going to win any prizes at the ball, and it is in rough shape and is not up to the usual standards of the lab. So this one I didn't want to see it in the landfill, and I didn't want to scrap it out for parts, especially with it working electrically. So it does get to live again. But yeah, definitely one of the rougher units that's come into the lab. But here we are. So this one's going to go back to its owner. I did talk to them, and they have another unit that's coming to me that they'd like that's in better shape. But this way I can get both of them back to them. And we'll be taking a look at a restoration on that unit as well. So if you like the content and want to stick around, hit the subscribe button. Definitely check out the comment section below. I do read all the comments on all the videos, and I'm there between video postings. With that, I will see everybody in the next video, and I got to get something else on the bench. Bye for now.